If you were wondering if it's just a conspiracy or anything like that, well, I mean, here's more proof if you need it. The World Economic Forum is introducing the black goo on their Instagram page, and they're calling it the slime robot. That's right. Old Graphene Ox is now known as the slime robot, and they call it a magnetic blob. I wonder why they're introducing this to the whole world. Well, because the whole world has, for the most part, already been introduced to it. At least half the population of the world has. They've been introduced to it all right. Now they need to know what exactly it's doing, right? And you might be a member of the website. Recently, I uploaded a video over there about graph again, because graph is being talked about again as being a cure for you-know-what. Yes, a cure for it, even though we already know what it's in, right? We know what it's in. Now they're saying it's a cure. I talked about this last year. I wouldn't be surprised if they start marketing it that way. Because remember, they're going to tell people that it can cure disease and it can do all these things because it's going to be transforming people. And now you have the World Economic Forum promoting it, talking about this quote-unquote new discovery. Give me a break. Get a load of this. So the magnetic blob, which is controlled by magnetic fields. We don't sound so crazy anymore, do we? Oh, right.
Let's put some ferrofluid on the plate. Ferrofluid is made of nanoparticles of iron, and when you apply a magnetic field to them, they follow the magnetic field lines in this spiky pattern here. The stronger the magnetic field is, the closer together the spikes form. So first, let me show you what happens when I move a regular magnet near the ferrofluid. You can see it just sucks it up to the magnet. Okay, now let's bring the superconductor up to it. Okay, watch it push the spikes out of the way as I bring it close. That's because it's opposing the magnetic field at first. Now, if I were able to get it closer, then it would lock in place and it wouldn't push the spikes out of the way. But if I push it any closer, it's going to go into the ferrofluid. Another cool thing I observed is that when you bring it near the ferrofluid, the spikes actually start to flow towards it. Now this seemed odd to me because there wasn't a reason magnetically why it should do that. So I tested it with just plastic that was cold, not a superconductor, and it did the same thing.
Bring it over to the point of the bolt and just gently drop it on there.
Okay.
In fact, you don't even have to touch it. It'll get pulled right over because of the magnetic field.
Wow, look at it building up. Whoa. That is so cool. It's turning, I don't even know how to describe it. It almost looks like if I touched it, it'd be spiky.
Watch this. Okay, wow. The magnet is actually drawing those particles. Keep loading it up. We're going to see how much fluid we can get on here. If you notice, you look really close, you can see they're like little spikes.
Yeah, that's what it almost looks like. If I were to touch it, it would be spiky. Clearly, I know that's not the case.
It's actually soft. It's still a liquid, but because of the magnetic field, it's actually taking on a different shape. Those little particles are actually little magnets, but they've been coated with a surfactant so they won't stick to themselves. But in the presence of a very strong magnet, they'll begin to take on these interesting shapes.
Oh, look, it's starting to get spiky even on the threading of the bolt.
Yeah.
That is super neat.
So it's fighting against gravity. The gravity's pulling it down. The magnet's pulling it down. Surface tension is trying to create these interesting shapes.
Sure.
But so it looks cool, right?
Yeah,
it's
looks
really
very
interesting,
cool.
Very cool. What would you use it for? Is the real question. And so if you have a hard drive with a spinning axis that you want to seal, you can use ferrofluid. You put two magnets around the axle, and the ferrofluid will form a seal around the axle. Or if you want to separate things that are non-magnetic, this is a copper penny.
Sure, but we know that it's only partially, not fully copper, right?
You're right. It's zinc inside and a little copper on the outside, but in either case, it's not magnetic. Okay,
right. Yeah, we know that. It's not going to stick to the fridge or anything like that.
How would I separate that out? We can use ferrofluid. So watch this. Load up my little cup with some ferrofluid. Just use the whole container. Just
like
you
just dump it in?
Yeah, just dump it in. It's okay. And if we, yeah, that's perfect. If we take the magnet and drop it inside, no great surprise, it's simply going to sink to the bottom.
Sure.
Now, here's where things might get a little bit messy. Watch out.
Woo!
Okay. If I take this super strong magnet and pull it away and put it underneath,
whoa,
the penny will float to the top.
Yeah, immediately.
Immediately. And if I take it away from the magnet, the penny sinks.
Wow.
If I bring it down to the ferrofluid,
and
penny
so
floats
that's
to the
just the
top.
force?
The ferrofluid is actually, and I can have you feel it. I'm going to put this magnet back under the plate, and I want you to reach in with your gloves and touch that clump of ferrofluid. What does it feel like? Describe
Oh,
that.
gel. It feels like a hard, gooey gel, and I can't grab it off here even though I want to.
The density of the material has changed in the presence of a magnetic field, and this is one way that recyclers can actually separate non-magnetic or non-ferrous metals from magnetic metals.
That is so neat, and yeah, you can't, I'm trying to even separate it,
crazy,
and it won't work.
It feels like Jell-O, it's really weird, but if we do take the magnet away, I'll try not to splash, it goes right back to a liquid.
Wow, that is really neat. So then this almost, in theory, can be reused as well, the actual...
It can, yes, absolutely, yeah.
Wow.
There's even some talk of using this sort of nanotechnology to target drugs. So if we attach a specific drug to the nanoparticles here, we could put it in an entire body and it would all be dilute. But if we target an organ with a strong magnetic field, we can actually cause all of the drugs to go to that one location.
So in theory, if you needed maybe a heart medicine that you didn't want going elsewhere,
in theory, yes,
there could be a magnet used so that we could
target that stuff using the tiny nanoparticles, and then take the field away. It disperses throughout the body, and you're fine.